Welcome to Real Chemistry. I'm Dr. Norris, and today we're going to be talking about the commutation relation. Now, before we get into what that is and why it's useful, let's just consider a bowling ball on a bowling alley. And this is going to lead into our discussion of the commutation relation, and then we're going to actually use the commutation relation. So first, this bowling ball. Imagine you've thrown a bowling ball down a bowling alley, and now you want to know what the momentum of that bowling ball is. We can measure that, no problem. We can measure the kinetic energy, we can measure the position. In fact, we can measure those all at the same time. And in the classical mechanics world, that poses no problem. I can know the position and momentum of that bowling ball as well as my measuring devices can tell me the position or momentum of that bowling ball. However, that's not actually true in the quantum world. So if instead of throwing a bowling ball down a bowling alley, I throw an electron, now for some observables, that is for some things I'd like to know about my electron, like position or momentum or kinetic energy, I can't actually know them at the same time with unlimited precision. There's limits on how well I can know information about those observables. Why is that? Well, when I take a measurement on a quantum system, I actually affect the system, and that's different than the classical mechanics world. So when I measure the position of the electron, I collapse its wave function, and that actually affects how well I could know its momentum, for example. So there's some observables that are linked in this special way in the quantum world. They're linked because I can't know both of them with unlimited precision at the same time. So there's this thing called the commutation relation, the title of this video, and that's what helps us decide, are two variables in the quantum world linked in this way, or are they not linked in this way? Let's take a look at what the commutation relationship looks like. Now, we're going to spend a lot of time getting ourselves familiar with this expression, and what it basically tells us is take any two observables. So this guy uses the observables A and B, and apply them to any function. We call this the test function. And first apply B, then A, and subtract that from the same function where we've applied A, then B. So we're just switching the orders we apply them in. And we're asking ourselves, do they commute? Can we switch which order we apply them in? And it turns out, if we can switch the order we can apply them in, then we can measure those two observables that correspond to those two operators at the same time with unlimited precision. If they don't commute, then there's a limit on how well we can know those two observables at the same time. So remember, we have a bunch of operators in the quantum world. We have an operator for position, for momentum, for kinetic energy, and that's what these A hats and B hats are representing, different operators that we can apply to a wave function. The nice thing about using the commutation relation is we don't actually have to have a specific function in mind. We just use this generic test function. And you will find that this makes things way easier. You don't actually have to take real derivatives. You just say, oh, that was f of x, and now we're going to say it's the first derivative. If you're confused about what I'm saying, hang on for a second, and we're going to do an example, and then I think it'll be more clear. So the commuter relation, this guy right here, is applied to a test function. And the way we know, then, if our variables is commute, is if it's equal to 0, if that relationship spits out 0, then they do commute, and we can know them to unlimited precision at the same time. So for example, say we apply the momentum and kinetic energy operators, and they commute. Well, that means there's no limit on how well I know my kinetic energy operator based on if I'm measuring the momentum at the same time. So I can measure momentum and kinetic energy of the electron at the same time if they commute, and that's no problem, just like it would be for the classical world. On the other hand, if it's not equal to 0, if instead we get something that's not 0, it's said that those operators do not commute. And since they don't commute, there's a limit on how well we can know them at the same time. So let's take a look at what this actually looks like. So far I've thrown some equations out there, but let's get a handle on actually using them. So the first question we're going to take a look at asks us to evaluate the commutator k hat x hat. And all that's saying is let's go ahead and plug in those two operators to this formula down there. And it asks the question, do they commute? And of course, if they commute or not tells us can we measure them at the same time to unlimited precision or not. So how do we do that? Well, I've broken this process down into 3 steps. And the first thing is we're just going to plug in our operators into our expression down there. So we start out with k hat, the operator for momentum, times x hat, the operator for position. And we're going to apply that to some test function, f of x. Now, the only purpose of that test function is to hang around and mark when we take derivatives, when we multiply stuff, and at the end we're going to drop that, and you'll see how that works. Okay, so in the commutator, we're going to apply the thing that appears first, a, second to f of x, and the thing that appears second, we're going to apply first to f of x. So I'm going to write down our first operator listed, which is kinetic energy, and kinetic energy is the operator h bar squared over 2m, and the derivative. And then we're going to put in our position operator, which is just x, times our test function, f of x. All right, so that's the first part of our commutator relation. We have our first operator and our second operator both acting on that function. Now all we're going to do is flip their order. So first I'm going to do the position operator, and then I'm going to do the kinetic energy operator. So, if we evaluate this expression, and at the end we get 0, they commute. If at the end we get not 0, they don't commute. So let's go ahead and start evaluating this. Well, when we take a look at this guy, we're taking the partial derivative of x times f of x. And if we think about what that's saying, that's taking the derivative of two functions of x being multiplied together, and that's where we need to use our product rule. So the only tricky part about this process is making sure you remember your derivatives rules. And the product rule comes up over and over again. So what that gives us is, of course, we just keep our h bar squared over 2m constant around, and now I'm going to write the derivative. Well, when we use the product rule, we get the first x, the first guy, so we just write x, times the derivative of the second. What's the derivative of f of x? Well, this is where it's nice to just have our test function, because we don't have to actually take the derivative of anything. All we're going to do is just write down f of x prime. That represents the first derivative. Okay, continuing the product rule, we just did the first times the derivative of the second. So now we need to do the derivative of the first, which is x. So that's just going to give us 1. The derivative of the first thing that appears there, x, which gives us 1, times the second, which is f of x. All right. Now we subtract from that our next set of operators. And here, notice, we're applying the operator x after we take the derivative. And so we're going to get our h bar squared over 2m out. And we're going to have our x. And then we're going to be taking the derivative of this guy. So when we take the derivative of f of x, again, we just get f prime. All right, so now let's see, does everything cancel out or not? Well, I can go ahead and distribute my h bar squared over 2m, x f prime of x. So there I'm distributing it to this guy, and then I'm going to distribute it to this guy, plus h bar squared over 2m f of x. And then that's all minus h bar squared over 2m x times f of x prime. That's one of our derivatives. Notice that this guy and this guy match. So one's positive and one's negative, and that means these guys cancel out to 0. They add together to give us 0. And then what we get is h bar squared over 2m f of x. And remember, that's all equal to our commutator, the thing we started out with, which was k hat x hat times our test function f of x. So now here we see our test function f of x on both sides, and what we're going to do is we're just going to drop that. And when we drop that, what we get is h bar squared over 2m equals our commutator, k hat x hat. So that tells us our answer then. When we apply the kinetic energy operator and the position operator in our commutator relation, we don't get 0. We get h bar squared over 2m. So the answer is they do not commute. What does that mean? Remember, that means we can't measure position and kinetic energy at the same time to unlimited precision. There's a limit on how well we can know position and how well we can know kinetic energy in the quantum world. Unlike in the classical world, where I can know the position and momentum as well as my instruments will tell me. Here, even if I have perfect instruments, there's going to be a limit on how well I know position and kinetic energy. Let's take a look at one more commutator. So this question asks, do kinetic energy and momentum commute? Is there a limit on how well we can know these observables at the same time? This is really asking the same question as our last problem. And so all we're going to do is we're going to follow those same steps, and we're going to plug in our observables, k hat and p hat, and we're going to apply them to some test function. And what that means is we're going to write down k first in this first part, which is h bar squared over 2n. This is our operator and the partial derivative. And then we're going to write down our momentum operator, which is negative I h bar, the partial derivative of f of x. All right, now we just flip the order of those operators. So first comes momentum, negative I h bar, partial derivative. And then comes our kinetic energy, h bar squared over 2n, partial derivative with respect to x of our test function. All right. So now all we have to do is evaluate this guy. Well, in both cases, we have these constants, and they don't affect what our derivative is. So we can go ahead and pull those out. So for the first term, we're going to get negative I h bar cubed over 2m. And then we have the partial of x, and then we have another derivative of x times f of x. And then in the next case, once again, we can pull out our constants and combine them, and we're going to get negative I h bar cubed over 2m. And then again, we still have our derivatives, the partial with respect to x, and then once again, the partial with respect to x. All right, so now it may be obvious to you right away that we're taking the derivative twice of f of x and multiplying it by the same constant. Those terms are already identical, which tells us they're going to cancel out. Let's just work that out in a little more detail. So we get I h bar cubed, this part's negative, over 2n. And when we take the second derivative, we take the derivative once and then twice of f of x, we're just going to get f of x double prime, the second derivative of f of x. Now here, our negative signs cancel out and we get positive. So we're going to add, once again, I h bar cubed over 2n. And then once again, we take the derivative twice of f of x, and that's just going to give us f of x double prime. And so you can see right away that those are equal and opposite terms. And so what they're going to do is they're going to cancel out to 0. And that means that our commutator, k hat, p hat, is equal to 0. That means they commute. That means we can know them as well as we want. We can measure them at the same time, and we can measure them to as good of precision as our instruments allow, and there's no restriction. It's just like the classical world. So thanks for watching this episode of Real Chemistry on commutator relations. If you have any questions, please ask them below. Please subscribe to Real Chemistry to get updates about future videos. Thanks for watching.